Oké. Nou, toch nog even, want het is de laatste keer dat jullie ernaar gaan kijken. Toch nog even, oh sorry. The last time you're going to look at it, the set of ugly equations. The only thing that I want to say, okay, that these are exact. That is always nice. It's a complicated mix of exponentials, and these exponentials have this one coefficient in there, the effective decay constant, effective attenuation coefficient. That depends only on the absorption coefficient and the backscatter coefficient. All right, but now let's put these to use and see look at some examples, and we'll see that we can draw some conclusions for the 3D case from that as well. So this is a calculation for a 1D, of course. So it's a slab of tissue with a finite thickness d. In this case, 5 millimeter thick. The intensity that is incident on the slab is 1 watt per square millimeter. It has an absorption coefficient of 0.1 per millimeter, and it has a scattering coefficient of 1 per millimeter. And what you see in the graph on the horizontal axis is depth into the tissue, and on the vertical axis you see all these parameters that we have been calculating. So we have in green the flux in the positive direction, in red the flux in the negative direction, in black F is the net flux, and in blue is the fluence rate. Is there anything that strikes you about this graph? Anything that you notice?
Well, all the lines, they sort of have the same shape or the same relation or dependency on the tissue depth.
Yeah, so that so it means that there are all these exponentials, and they all have all these exponentials, all these expressions have the same decay coefficient. And therefore they will look very similarly. If you look at let's say the green curve, the flux in the positive direction, what do you expect for the value at a tissue depth of 0? So that's basically at the left boundary.
I get. Wait, no. Does it make sense that there's only forward flux at the entrance? So at tissue depth 0, you are at the surface of the tissue, right?
Exactly. Yeah.
So if you hit the tissue. I guess it makes sense that you can't backward scatter when you're at the tissue, the surface tissue. So forward scattering should be 1.
Yeah. So basically, at the boundary, the forward flux is just the light that enters, and the backward flux is just the light that escapes. Right.
Oh, okay. Yeah. Mm-hmm.
So the value of the flux in the forward direction at exactly 0 depth has to be whatever you put in, because that is the only source of light. So it has to be this 1 watt per millimeter. Has to be here. And then if you go to the end, to the 5 millimeter depth, then you see that it decays, but it doesn't go to 0. So that means that some light apparently escapes the tissue on that other side as well. On the other boundary at 5 millimeter, then any light, any flux in the forward direction is the light that escapes.
Yeah. Then why does the red flux start between at like 0.65?
Because that is essentially the light that escapes on the entrance side. So light goes in the positive direction. So you have a light source somewhere over here that sends light into the slab in the plus x direction, and then at the boundary you're going to look at, okay, how much light is going in the plus direction, so that's entering, and how much light is exiting in the minus direction, and that is the red curve. So that means in this case that 0.65 watts per square millimeter is exiting the tissue. It's being reflected. And in the same way, if you look at the other.
Right. Yeah. So it's it's actually reflected the light which you're looking at. Oh, okay. Yeah.
And at the other boundary, at 5 millimeters, because there is only a light source on one side and not on the other side, then at the other boundary there cannot be light entering from that side. So the flux in the negative direction at the other boundary has to be 0. That's what you see here as well. So here it is neatly 0. Then of course we had the net flux, which was the difference between plus and minus fluxes. So that is then the black curve. But if you now look at the blue curve, the fluence rate. So let's look at the fluence rate at the depth of point. I mean, it's not really necessarily in the graph, but 0.1 millimeter.
So at 0.1 millimeters into the tissue.
Yeah. So what would trying to read it myself? What would be about the fluence rate there?
Something like 1.6, I think.
Yeah, something like that. Okay. So 1.6 watts per square millimeter is more than the 1 watt per square millimeter that you put in. And do you remember what the significance of fluence rate was? What was the why are we eager to calculate the fluence rate? So if I multiply the fluence rate with the absorption coefficient, I get the amount of power that is absorbed in the tissue per unit volume. So that means that in this case, I have the absorption, the amount of power that's being absorbed just below the surface is more than what I would expect based on what I put in. So I put in only 1 watt per millimeter, yet just below the surface, the amount of power that is absorbed there is about a factor 1.6 higher in this case. And this is and of course, so you so can you explain the mechanism? Why would that be? I mean, it's no rocket science, of course.
Could you maybe go back to the formula for the fluence rate then?
No, it's not in the formula. You don't need formulas. It's just that no. So the intensity is only the light that is coming in one direction, but just below the surface you have there's also light that comes from deeper within, but going back. So there's two. So at just below the surface there are actually 2 contributions. There is the light that you put in yourself, but there's also the light that has been in there already, but is now coming back. That builds up. So therefore you have more light available there. That actually used to be people have made mistakes for that. So for example, when I think it was in the bladder or something that they wanted to do some laser damage. So some tissue that was cancerous tissue, so in the bladder, and they wanted to go in with the laser and then burn it away. So they calculated how much power power the laser should have in order to make damage to the tumor tissue, but not too much on the surrounding tissue. That was basically the goal. But they calculated that only based on the input intensity, and it did not account for the light coming back. So in the end, what it turned out that since there was more light, there was also more damage. That they really also damaged healthy tissue around that tumor. And then, of course, later on, the people quickly realized what was going on, and then so all was fine then. But in the beginning of these laser therapies, that was actually a mistake that was made. And of course, this is you can see it clearly here in the 1D effect, but this obviously also happens in real life because it is just the sum of the light that you put in and the light that is backscattered from deeper regions.
But a question about the fluence rate, because so in your example, they hurt more tissue in the bladder because of they didn't calculate the fluence rate. Yeah. But you do not necessarily, or the light that is coming back, that's not necessarily focused on the bladder, right? Because it can be scattered in all directions. So therefore, it is not that all the light is concentrated when it returns, but it can be randomly distributed, right?
Yeah. So it's not all the light that comes back. It's just a fraction. So basically, you have so just below the surface, you have let's say a direct contribution of the light that has just entered, and then everything that is not absorbed in that first pass is bouncing back and forth in the tissue, and some fraction of that will go through that volume again. So not all of it, but but that fraction, it can be a lot. If the so let's say if the probability of scattering is really high, yeah, then the probability that after passing through the volume the first time, the probability of it being scattered and then going back is also high. So for a high scattering coefficient, that contribution can be pretty high. So it depends a little bit on the properties themselves, but it's not.
And the values that you've used here are regular or realistic properties.
Yeah, that's realistic. Yeah.
Okay. Yeah.
No, actually for the not for the intensity, but that doesn't really matter. That's just scaling. There's one nice another nice thing for it because if you now remember the definition that we had for reflectivity, so that was the flux in the backward direction at the incident boundary. If we divide that by the incident intensity, that was the reflectivity, the fraction of the light that is reflected from the tissue. So if you now write the equation for the fluence rate at the boundary, so that is V0, is the sum of both fluxes, so the flux in the positive direction plus the flux in the negative direction. Well, the flux in the positive direction, by definition, was the incident intensity at the boundary, and for the other one, for the flux in the negative direction, we can write reflectivity times input intensity. So if you combine that, you see that the fluence rate at the surface, or let's say just below the surface, is the incident intensity times 1 plus r. So that actually quantifies this build-up factor. And the really nice thing about it is that this reflectivity you can measure. So if you have some kind of second probe or second fiber next to the one that you want to do your therapy with, for example, you can first measure the reflectivity of the tissue, and if you know that, then you can account for that effect by that. So it actually turns out quite nicely then. Then a second example is a very thick slab. So the slab is so thick that I've put the horizontal axis on a logarithmic scale. 100 millimeters thick. There is no absorption in the slab, so only a scattering coefficient of 1 per millimeter, and there's an incident intensity again from one direction of 1 watt per 1 watt per square millimeter. So now for the light, there is only 2 options. Because there is no absorption, the light can only be reflected or be transmitted, or forever bounce back and forth within the slab. But there is no loss because it's not absorbed. So in that case, the net flux is going to be 0 because since there's nothing. So we had the equation that said that the net flux, the change in net flux, the FDX, was equal to the absorption coefficient times the fluence rate. if the absorption coefficient is 0, then the change in net flux is 0. So the net flux is 0, which implies, and that follows also from the equation, that the flux in the positive and negative direction are equal, and that gives us the maximum fluence rate attainable. So in this case, because of that back and forth scattering of light, you get an identical contribution to the fluence rate just below the surface. So this is basically the limit. The limit is that it is two times higher. This is of course totally unrealistic, but this one is this is quasi-realistic. A little bit careful. So now on the horizontal axis is not the position in the tissue, but the thickness of a tissue slab. And what is calculated here is the reflectance of such a slab as a function of the thickness of the tissue. And as you can see, that if the tissue is very thin, then the reflectance is very low, which means that most of the light is transmitted to the other side. If the slab gets thicker, more and more light gets reflected as well. And then at a certain point, if the thickness of the medium goes to infinity, if it goes to infinity, there can be no more transmittance. So then the light is in this case either absorbed or reflected. So we have a modest absorption coefficient here, so it can also be absorbed. But it means that the reflectance itself goes to a limiting value. A limiting value, you can calculate that value. That is m. That turns out to be m minus b. So expressed purely in terms of the absorption and the backscattering coefficient again. In this case, for this example, it's this value. Infinitely thick seems a little bit weird, but in many actually in many applications that it's a pretty good assumption, because if you look at how far light can travel when there is absorption, compared to how big an organ is, or how big the tissue is that you're looking at, and then you can sometimes actually just regard it as infinitely thick.
I do not totally get why the reflectance at infinity does only go to 0.64, because I would think if you have a very thick slab, that then the light wouldn't be able to, or at least the chance will be really low that the light comes out in the other end, right? Because it has so many scattering events possibilities in between. So I would think it goes closer to 1, but that's not the case.
No, that's not that's right, but that's the case because there is an absorption coefficient.
Oh, okay.
So that part is just lost, is just absorbed.
Okay.
So if I would set the absorption coefficient to 0, then the limiting value would be 1.
Yeah. Okay. Yeah.
Then essentially that is the only way that the photon can end up.
Yeah.
But now,
okay.
because there is a small absorption, it is.
Yes.
Yeah. Okay. So so then so if you then look at that semi-infinite medium, then also in the equations they become a lot simpler, because the d that was in there then can be taken to infinity. So a couple of results for that special case are that the reflectance goes to a limiting value of m minus b, and again the definitions of m and b are below there. The transmittance for an infinitely thick medium is 0, because there is no other end. And the equations for the fluxes really simplify to single exponentials. So the flux in the forward direction, the flux in the backward direction, the net flux, and the fluence rate is here as well somewhere. Yeah, and the fluence rates there are all just simple exponentials, all with this effective attenuation coefficient. So this beast over here as the coefficient in the exponential. So that simplifies it. All right, I want to stop now here for the with regard to the transport theory. So the main message here is indeed that the 3D version is really hard to solve. The 1D version is solvable, as you saw. and it gives you some things that some insight for how it behaves in 3D as well. So that, but the thing itself is really hard to use. So what is possible is to use the diffusion approximation to the radiative transport equation. It is generally so basically the same assumptions. We're going to use just transport of power and not electric fields or whatever. And conceptually, what it does is it regards the propagation of light as a diffusion process. So the photon energy diffuses down a gradient, down a concentration gradient of photon energy in order to balance it, just like in a diffusion process. It's quick. It's generally useful. I'll briefly indicate that it can be derived from the radiative transport equation itself. So it has some physical basis. But there's also because the name, as the name approximation implies, there is also some limits. It's not good if you're near a light source, and it's also not so good for tissues that have really high absorption. So let's say for blood, for example. But still. Since it's a diffusion process, it also actually implies that there is no real preferential direction for the photon. Think diffusion, think Brownian motion. There is no real preferential direction for the movement, unless there is some kind of gradient. In that case, the movement is down the gradient in order to get that equilibrium back again. Also, that this no preferred direction of the movement is in case of scattering, you can associate it with what the scattering event does. So a scattering event changes the direction of photons. So let's say you shine in a laser beam in which the photons at first all have the same direction. So that would be something that is in contradiction with this diffusion approximation. But as the light scatters many times, each time under different angles, after a certain while, the directions of the individual photons become kind of randomized. Then in that case, there is no preferred direction anymore, and then the situation is compatible with this diffusion picture. So you need in general, so that is also the reason why it's not so good near a light source, because there the photons still have really preferential directions, but after many scattering events, that is lost, and then this diffusion picture becomes realistic. That's also the reason, the same reason why the high absorption is a limiting factor, because if the absorption is really high, then the photons do not get a chance to experience many scattering events. They do not get that randomization. They are absorbed after a few scattering events. So then the light that propagates has still this preferential direction. So conceptually, that is why the drawbacks are there, because the photons still have their own direction. So again, we'll consider the fluence rate, so the amount of power flowing through an area at a point R in the tissue in all directions, watt per square meter, is of course the same as the amount of energy per unit time through that area, joules per second per square meter. So what we now can do is define a concentration gradient of optical energy. So a concentration of optical energy, so that would be joules per cubic meter then. And now let's see if we can tie all these things together. First, the optical energy flows. It moves at the speed of light in the medium. So that is C is Z, C0, the vacuum value, divided by the refractive index, which has units meters per second, of course. We can tie the so the
Dirk, your audio is completely messed up. It's pretty much inaudible, sorry.
Well, we do hear you, but the audio is really weird. It's kind of lacking and yeah, kind of robotic.
Yeah, it is completely inaudible for me. So I can hear you, but I have no idea what you're actually saying.
No. Okay, what to do? Can you hear each other? Yeah, okay. Okay. So from my side. One second. Okay. Is it better?
It's still pretty messed up.
We'll try it like this. Is this better?
Yes.
Yeah. All right. Then we'll do it like this. Okay. Were you asking a question, or were you just pointing me out to the bad sound?
I was just pointing out the audio.
Okay, great. Then I'll just continue. So we have then the fluence rate as a measure of the concentration of photon energy, and then the goal is then to describe the diffusion of light, the movement of energy of photons down a possible concentration gradient, so down a fluence rate gradient. That is given by so diffusion processes are given then by a fixed law of diffusion, which in general form reads this. So on the left-hand side, you have a net flux down a concentration gradient, dc dx. So this describes the flux down the gradient, and there is a proportionality constant, diffusivity, that tells you how strong this process is. So if you look at the units, so in our case, the net flux would be in watt per square meter. The concentration would be in joule. After you take the derivative of the concentration, it would be in joule per meters to the fourth power. So that is the gradient was, or the concentration was per cubic meter, and then taking a derivative to x gives you an extra per meter there. So that means that the coefficient in between has units square meters per second, which is the usual unit that you find in these diffusion processes. That's called the diffusivity. What we can do is for light is include the speed of light in that. So then that allows us to define then a factor d, a diffusion coefficient, which then has units of length, unit per meter. Yeah, so diffusion coefficient. So if we then use the symbols that we had before. So for the net flux we had F. For the with the substitution of for the concentration use this fluence rate substitution. Then C is included in the diffusivity. So then we end up with this this formulation of Fick's law for the net flux on the left-hand side, derivative of the fluence rate on the right-hand side, and a diffusion coefficient that ties them all together. So basically the reasoning now is that if we can describe the transport of photons as a diffusive process, then this is the form of Fick's law that does that. So net flux and fluence rate and a new coefficient, a diffusion coefficient D. I won't fault you if you don't immediately remember, but we saw this form in the before the break in the 1D case. So they're on the other side of the equations, but there we had an equation that expressed the derivative of the fluence rate as a function of the net flux. So these two equations are, as you can see, very similar. So that if you rearrange it a little bit, that means that this 1D, if we now regard this as a 1D diffusion equation, as a 1D form of Fick's law, then that kind of suggests that the diffusion coefficient is going to be 1 over, in this case, mu A times mu A plus 2 times the backscatter coefficient, mu B. And we had this little rearrangement for that. So we can also write it as 1 over the absorption coefficient plus the mu S times 1 minus G. So it's no definite proof, but this gives a little bit of a hint how the diffusion coefficient is going to look like. Yeah, and just it's for completeness. Then we can also express the effective attenuation coefficient in terms of this diffusion coefficient. Right. So this is a little bit a what if kind of derivation. So what if we can describe photon transport as a diffusive process? Well, then this would be the result. But that's a little bit hand waving. So there is also a way to get to the diffusion approximation from the radiative transport equation. So this is the transport equation again, just for your so that you remember how complicated it was. So you could, if you now assume that the medium that we're trying to solve this is infinite in all directions. It's infinitely wide. We're somewhere in the middle, and it has complete spherical symmetry. So no inhomogeneous, nothing. So everything is completely spherical symmetry. What we can then do is make a series expansion of all the terms in here. So we can switch to a spherical coordinate system, and then try to make a series expansion in that coordinate system of the terms in here. So that means that the radiance is expressed as a series expansion of spherical harmonics, and the phase function, which is just a flat function, as an expansion of Legendre polynomials. So these are all functions that keep that symmetry. So it's basically just like making a Taylor expression, but now you do it in spherical coordinates. So the spherical harmonics that are these functions here. So you basically build up the radiance as a sum of all of these components. And for the phase function, these are the Legendre polynomials. There too, you just write the phase function as a series expansion of these polynomials. So if you do that, then simple expression for the radiance is not there, so I'm not going to bother with that. It is worthwhile to look a little bit closer to how that looks for the phase function. So that means x is cosine theta. It will be a function of cosine theta only. Then the phase function as a function of x is this series of Legendre polynomial of order n. That were the functions in that table on the previous slide. They are all weighted by well, something that depends on the order number and by some coefficient g of n. And you can calculate just more or less similar to how you would do it for a Taylor expansion. You can calculate these these G's, these moments, Legendre moments G's, from the phase function itself. So if you have the phase function, you multiply it with the polynomial of order n, and then you calculate this overlap integral, and that gives you the coefficients. So actually the expansion of the phase function in terms of these Legendre polynomials is pretty straightforward. Yeah, so if you write it in terms of theta and phi, then it will be will look like this. If you look at the zeroth order version, then you have to take the zeroth order Legendre polynomial. That happens to be just so p0 of x is 1. So if you then look at this equation, then it says that that g0 is 2 pi times the integral from -1 to 1 of px dx. Px being the phase function, x being cosine theta. That basically tells us is just the integral, just the integral of the phase function. And by definition, that was unity. So that means that that for g0 we end up with unity because the phase function is normalized. For n is 1, we have the Legendre polynomial p. Oh, that should be a 1 then. P sub 1 is x or equal to cosine theta. So if you then look at the equation here, then it says the integral of x times the phase x times the phase function dx, or cosine theta times the phase function sine theta d theta, which was the definition of the scattering anisotropy G. So G1 is just our familiar scattering anisotropy by its definition. And of course, you can make this list longer for a higher order for higher orders. The funny thing about these Legendre polynomials is that that if you make this expansion in spherical coordinates, then you end up with a couple of a series of which are called similarity relations. And these similarity relations, they hold for example, for the fluence rate, or they hold for reflectance. And they tell you that, maybe it's easier to put up this example immediately. They tell you that that the values of US and the values of G1 themselves do not matter, because they only appear in these products. So if you have a tissue with scattering properties μs, and then coefficients for the phase function G1, G2 up until Gn, that will give you the same reflectance, these tissues, if you have another set of optical properties. So μs star, G1 star, G2 star, Gn star, you will get the same reflectance, the same fluence rate, the same all when these equalities hold. So it is not the individual values of the scattering coefficient and G1 that matter. As long as the product of μs and 1 minus G1 is the same for both of these sets of parameters, you will get the same reflectance. And if you have an n-term expansion, then you get n of these similarity equations. Actually, the first one is so important that it gets its own symbol. So μs times 1 minus g is called the reduced scattering coefficient. μs prime, it gets a little prime here. Now the way to derive, and you felt that coming a little bit, I guess, because I alluded to the Taylor expansion. You get the diffusion approximation, so that same set of equations that we had before, by doing this development and keeping only the first and the zeroth and the first order of the expansion. So you have this complicated spherical function for the radiance, for example, this complicated function for the phase function. Now you're going to keep only the zeroth and the first order of the expansion to solve this equation, and then you end up with this diffusion approximation again. Of course, this truncation results in a lot of limits of validity because you throw away a lot of information. But the good thing is that there is only one relation left, namely for μs prime. So that means that in this diffusion approximation, the value of μs and of g themselves are not important. The only thing that determines the outcome is μs times 1 minus g. So only this reduced scattering coefficient is of importance. The result is then this diffusive these equations that resemble the diffusive process of photon energy. This is just the same equations again, so it's not necessarily to repeat. What is nice from this is that you can actually get an expression for the diffusion coefficient from this whole derivation. If you do the derivation and you see what ends up for the diffusion coefficient, then you find that it is given by 1 divided by 3 times μs prime. A little more remark on that later on. But the first thing is that what is important is this reduced scattering coefficient. So let's consider a photon trajectory. So a photon is traveling, is scattered at this site number 1, changes direction, takes a short propagation step where nothing happens, then takes a propagation to 3 where it is scattered, to 4, etc., etc. So this way the trajectory is built up. So let's say that this tissue has a high scattering anisotropy, which means that the average cosine of the scattering angle will be a small number, which means that the deflection angles on average will be very small. So that means that this photon takes a lot of small scatters under most of the times on the small angles, sometimes under a larger one. It can happen, but most of the time it's just small angles. And also we know that from the definition of the scattering coefficient that the mean path between these scattering events is given by 1 over the scattering coefficient, 1 over μs. So that is if we zoom in on this path, that is what happens. But essentially, we were looking at bulk tissue. We're not that interested in the dynamics of this individual path. What happens is that the photon went from here to here. And that it had an initial direction this way, and that it now has an exit direction that way. So what we could also do then, for example, is take an equivalent photon path where longer steps are taken and larger angles are experienced, and get more or less at the same result. So here too, the photon is scattered, is incident here and is escaping about here. But it has taken longer steps, and it has been scattered over larger angles, but the net effect is the same. So this gives an equivalent path. And if we now pick the distribution of the deflection angles in such a way that it is totally isotropic, so every angle is equally likely, then we can get an expression for the average length of these longer steps, and that turns out to be this 1 over μs prime now. So basically, what we have here is that we have 2 equivalent photon paths. The one has short steps with mean path length 1 over μs and small scattering angles, and the other one has longer steps with mean length between the steps of 1 over this μs prime, and all the scattering angles are isotropically distributed, so all are equally likely. So that is the equivalence between these 2 situations. Okay, I'm gonna show you some results, some key results from this whole exercise, and we'll try to tell you how it is applicable, and that is then how we will end for today. If we take a point source inside an infinite medium, so the medium is infinitely wide and infinitely deep in all directions, and we have a point source, a perfect point source somewhere in between, in there, let's say at the origin, then we can calculate, we can solve the fluence rate at some distance r from that point source at some time t. And that gives this expression. So in this expression are of course the distance. There is this diffusion coefficient that depends on the optical properties. There is time t here, and there's the speed of light c, and an absorption coefficient. C times t, that's speed times time, is a length. So we can write this. We can write this as function of a length. L, path length c times t is L, path length L, away from the source. And also in this case, in this vector, this exponential vector here, it's an exponential of minus mu a times L. So that is a Lambert-Beer kind of expression. So normally we have usually we would look at Lambert-Beer just as a cuvette of thickness L, where the light passes through, and this expression tells you how much light is absorbed. This is more or less the same thing, only that there now is not a straight path through a cuvette, but a very convoluted path through the tissue. But still, the absorption simply takes place along that trajectory of the photon, and this term accounts for that. This was time resolved. If we look at it in a steady state, the equation becomes a little bit simpler even, as given here. This is an important equation. So again, we get an exponential decay term with an attenuation coefficient, an effective attenuation coefficient, which is a function of the absorption coefficient and a function of the diffusion coefficient. The diffusion coefficient was 1 over 3 times the reduced scattering coefficient, so we can include that here. And then this is the effective attenuation coefficient. There's a little bit of controversy. You may have noticed that I used two definitions of the diffusion coefficient in this presentation. So one was here on the left-hand side, which includes the absorption coefficient, and the other one is exactly the same, but it does not include the absorption coefficient. The controversy stems from the fact that if you do the derivation from the radiative transport equation that includes an absorption term, an absorption loss term, then you end up with the absorption over here. If you do the same derivation for a medium that has no absorption, then it does not end up. And sometimes you do that because you can always add absorption later when just by taking the absorption along the path, as in Lambert-Beer, as is in this convoluted way. So it depends a little bit on how you start. The controversy is hard to solve, so I'm just going to be the judge of that. This is the right solution. The diffusion coefficient should not include the absorption coefficient. My argument for that is that if you this is the only way in which you can unify the time-resolved and steady-state diffusion equations. It's a long story. I'm not going to go too much into that, but you can imagine that if you have something that is time-resolved and you integrate it over time, then you should get something. Then you should get a steady-state solution, and that only works if you use this definition. So I'm going forward with this one. This was all for an infinitely wide and infinitely deep medium, so that is not very practical yet. So let's make it a little bit more practical by looking at a semi-infinite medium. So there is one boundary. We have a tissue here that has certain optical properties. We have a medium over here where nothing happens. So light enters from that medium. It can have a certain refractive index, but it does not scatter or absorb light. It is just a medium. Now you need, if you want to use this geometry, you need some boundary conditions, literally, and the most important boundary condition is that once so you shine light in, let's say from the medium in the tissue, some light may escape again, be reflected, but the condition is that because nothing happens in the medium, the reflected light cannot re-enter the tissue. So once it's reflected, it's gone. That is the most important boundary condition. Now, in that if you keep that, if you adhere to that, then you can actually calculate fluence rate. You can calculate fluxes at the boundary using Fick's law. If you have the fluence rate, you can apply Fick's law and calculate the flux at the boundary. If you have a flux at the boundary, you can calculate reflectance. So you can calculate something that you could actually measure. And if you want to make it really complicated, then you can even account for the media on both sides of the boundary, having different refractive indices. Modeling a laser beam that shines light in the tissue is not that easy. So so to model that, we just take a point source inside the tissue, somewhere over here at a certain depth. And in order to satisfy the boundary condition, we have to define a mirrored source somewhere here as well, in order to make sure that boundary conditions are satisfied. So instead of a laser beam, we have two unrealistic light sources, one inside the medium and one above the medium. Now you can using that, you can calculate the reflected light from the tissue as a function of radial coordinates. So that is the distance from the quasi point where light enters to some radial point along the surface. And the equation for that, so I'm not going to do the derivation, I'm going to just show you the equation, looks like this. So again a quite ugly equation, it may seem, but if we look a little bit closer, then we'll notice some things. So there is distances in here, R1 and R2, that are just geometrical distances from that fake point source, which is located at a depth Z0 to some point on the boundary. And for the R2, that's the same thing, but then for the other source that was floating above the boundary. So these distances are expressed in terms of Z0, which we had in here as well, and D, the diffusion coefficient, which was a function of optical properties. The effective attenuation coefficient already was a function of optical properties, so that's good. We can essentially pick the source position. That does not really matter. So a convenient choice is to put it at 1 over mu s prime. It says mu s prime here, but it's a distance, so it's 1 over mu s prime. And then in order to satisfy this boundary condition, that enforces that the mirror source above the tissue is placed at this distance. So again, Z0 is now a function of optical properties. D already was a function of optical properties. So basically, we're now expressing this whole thing as a function of optical properties. So even though it's an ugly equation, the only parameters that go in there are the absorption coefficient and the reduced scattering coefficient. And that's good news, because that means that we can do a measurement. We can measure how much light escapes at a certain distance, or at a couple of distances, and then we can invert this equation numerically in order to retrieve the absorption and the reduced scattering coefficient. So this, even though it is a little bit ugly and there is a lot of assumptions underlying it, this is actually a quite useful equation. If you look at these chapters 16 and 17 with the applications, you will encounter it again. One remark over these boundary conditions. So you have to. So a physical boundary condition is that the light cannot re-enter, but other than that, you can also impose some mathematical boundary conditions that are all equivalent. They are all physically plausible, but if you do that, they all lead to slightly different outcomes. And to illustrate that is this graph. So what I calculated here is all the reflected light. So the previous expression had reflected light at some location on the tissue surface. If we add up all these surfaces, we get the total amount of reflected light, and that is what is calculated here. It is that's here on the vertical axis. It is plotted as a function of absorption, of the ratio of absorption and reduced scattering coefficient. And the different curves are for different boundary conditions. So the orange one is the 1D transport equation, which we did before the break, and then these a little bit elusively labeled curves are different boundary conditions. And as you can see, the outcomes, so they have the same behavior, they have the same overall effect, but it is slightly different. That may seem a little bit strange that this happens, but because the boundary conditions are equally valid. But this is just a result of this truncation, of the fact that you do this development in spherical harmonics and Legendre polynomials, but you only keep the first and second order. So even though and that introduces some inaccuracy, and that inaccuracy is exposed in this case by using these different boundary conditions. Of course, people have been wondering what that's all good and nice, but one of them has to be the best. That can only be found out by experiments. So we actually tried to do that. We measured this reflectance as a function of these absorption and scattering coefficients. A couple of experiments. So this is the black dots are a series that is measured with a very high reduced scattering coefficient. The open dots are measured at a lower value of the reduced scattering coefficient. And as you can see, the result is that the accuracy of the measurement is not good enough to say something about this. So really, in terms of describing these measurements, it really does not matter which of the formalisms you pick. The nice thing is that if you use these, they all depend only on this ratio that is here on the horizontal axis. They only depend on the ratio of mu a and mu s prime, so not on the values of the absorption coefficient and the scattering coefficient and the anisotropy individually, only in this ratio. All right, so this is then a quote from the book, from that chapter that has all the derivations, and in the end the author is a little bit discouraged, and he asks, well, I'll just read it. One may wonder whether light propagation can be adequately treated by photons whose propagation, including scattering absorption, is described by transport theory rather than wave theory. Transport theory means that you use that you consider just the transport of power, and wave theory is where you would actually try to solve Maxwell's equations for these complex geometries. Diffusion theory can be derived from general principles using macroscopic tissue properties. That means the scattering coefficient, the absorption coefficient, and is therefore a beetje een open deur, expected to hold within the restrictions involved in the approximations. Well, the restriction was that too close to a light source, it will not work. If the absorption is too high, it will not work. Requirement is that the optical mean free path, so one over, so basically the path between collisions or absorption events, is much smaller than the typical dimension of the problem. So that has to be less than the distance between where the light enters and where it escapes, or where a boundary is or a source is. And furthermore, or actually that implies that the photon should be scattered many times before it is absorbed or it leaves the medium. That's all still a little bit vague. So what is then the limit? Well, there is a rule of thumb for the length that the photon should have traveled. It's given by this, so at least 4 times the reduced scattering coefficient. So if you have light entering at a location here, then only when the photon has traveled at least this distance, you can reasonably assume that you can use this diffusion approximation as something to describe the propagation. So what's then the conclusion of this whole exercise? well, for the radiative transport equation, it is exact. So if you can solve it, then of course you should use it. That can also be numerically, of course, but that's difficult. You can only do that in the simplest conditions. And then there is the diffusion approximation to this transport equation. It's much simpler. You can get analytical solutions for reflectance, for fluence rate, even ones that you can invert easily, so you can do measurements and then extract optical properties. But the drawback there is that it is very limited in its range. So you cannot use it at short source detector separations. So finally, I'm not going to ask you to answer that, but I'm going to ask you to ponder on these questions, because these are the important questions that remain from today. All right, that's it for today. Any questions or remarks at this point? Okay.
I think I'm good.
Okay, excellent. Well, in that case, I wish you a good weekend. Take a look at the assignment. If there is anything unclear, please do not hesitate. Just send me an email, because I think it's a fun thing to do, and I don't want you hung up with some stupid numerical problem.
No,
Okay.
of course. Yeah, thanks.
Okay.
Thank you. Bye.
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 Oh, just to mention it, your audio sounds a lot better without the headset.
Yeah, I think
I'm
it's
not sure.
No, it's on battery. I guess the battery was empty.
Oh, okay.
And otherwise, we'll do it like this.
All right. Thanks.
Okay. All right.